Thanks, John. Well, and thanks for also thanking the organizers. I was going to do that, but then, okay, so. Okay, man, then maybe at the end someone will thank the speakers, but not me. It would be very bad. Okay, so this is joint work with Farzad and Asghar. Both are here, and so been working with Farzad for quite a few years now, 4 or 5 years, kind of spectral stuff. So, but this is different. So nothing is non-commutative. So first of all, relax. I mean, commutative people should relax now. Everything is commutative. There's no non-commutative torus also. Andre, you should also relax. I mean, so we are back to. So, okay, so it's about a metric which is kind of, I mean, plays a very important role in GR. I mean, that's Robertson-Walker metrics. And so you ask, okay, so metric is this kind of predominant metric in GR, but you ask some hard questions about it, and then calculations get really hard. And so that's how we got interested into that. But I want to, so this crowd is really very strong that has survived all these 2-3 weeks. So I just want to start quite relaxed and just give you a little bit of background. And the background, it won't be operator algebras, it won't be even physics, it won't be geometry. So I just want to go back to number theory, which is kind of the roots of some of the things that we are doing actually, and all of you, some of you actually been doing, goes back to really analytic number theory, and I want to go back to that. So let's just start from there. So now, I know it's a hard question. So imagine you want to compute this function at this value t equal to 0.1, at t equal to 1/100. Okay, so the function is a very famous function. Of course, you know that's the famous theta function. It's one of the families of series of theta functions that was defined by Jacobi, right? So you're summing over all integers. Those exponentials, they go by n squared instead of n. And then you want to know the value of this theta function at t equal to 1/100. So it's very simple to see that. I think to get it to 1 decimal digit, you have to add 21 terms. So if you don't have any technology, I just have computers at hand and just summation of computers, so you have to add 21. But if you want to have it to maybe 5 decimal digit, then you have to add many, many terms. And that's, that increase quite fast becomes intractable even for computers without some smart kind of idea behind it. Okay? So, okay, so maybe I ask. So I know it's not a fair question. Any guess for what the answer might be? Sorry? The question is, compute this to 1 decimal digit. I mean, compute it to just, no, it's not 0. It's not, it's very good. Okay. It's a number that, no, it's not 0. There's no cancellation. No. You have to have some deep ideas about this. But once you have it, then you can calculate it up to 130 decimal digits without any calculations. Okay, so that's, you can calculate to 130 decimal digits without calculating anything. So the answer is 10 up to 130 decimal digits, around that order. But let me tell you why. It's not easy to see that the answer is 10, but okay, I'll tell you why. Okay, so before going that, so this is what I said. Now it's written there, so I don't need it. Okay, so let me tell you what's the idea. The real idea behind the calculation is a deep fact. It's this modular equation that's due to Jacobi from 1828, actually. It's almost 200 years old. So Jacobi's inversion formula, or Jacobi's modular equation, says that theta of t is equal to 1/√t theta of 1/t. So t is think of it as a positive number, defined, the theta defined for all positive numbers. And when t goes near 0, that's 1/√t, and then there is theta of 1/t. So this equation is very important. Okay, so this is the kind of backbone of Riemann's functional equation for zeta function, for example. And similar equations are responsible for functional equations for all kinds of Dedekind zeta functions. So this equation is very, very important. And if you go to complex plane, upper half plane, it shows that theta function actually is a modular function and a lot of other things. But for the moment, we just stick to that. And so then using this equation, you notice that, of course, theta of 1 over t is really exponential decaying, and then the power is minus 1 over t. So that's decaying really, really fast, faster than any polynomial power near t equal to 0. And then you can see that this gives you very, very good approximation. Indeed, 1 over root t, as Dimitri said, gives very, very good approximation to the value of theta function. So, and you can just easily convince yourself that this order of this thing, if t is 1 over 100, it's going to be very, very small, as order that you wish. So indeed, if you write many, many, many zeros, still you're okay. So you have computed it to really high order. So this is really good. So that's how these calculations actually are done in this business. So the backbone is, in this case, modular equation. Okay. So I can turn it around, and I can say that then Jacobi indeed was the first person who calculated this asymptotic expansion of the heat kernel, actually, because this is really the asymptotic expansion for the heat kernel on the right-hand side. This is essentially heat kernel for, okay, so there is some part, but this is essentially heat kernel for Laplacian and the circle. 1 over root t is the dominant part, and the rest are 0. There's nothing else. So that's what this equation tells us. Okay, now to prove that equation, again, another technique that I will use later, so let me just tell you, is Poisson summation formula. So this is this wonderful formula to sum all delta functions at all integers. You get the same as summing all exponentials, and the equality in the sense of distributions. Okay, both sides are highly divergent things, but as distributions, they're absolutely fine. You apply this to any function, you get some convergent sums, and if the function is rapid decay, you get convergent sums, and then everything is okay. So this is the, you use this Poisson summation formula, apply it to Gaussian, and knowing that the Fourier transform of Gaussian is again Gaussian of certain type, then you get that formula, that Jacobi inversion formula that I wrote down for you. Okay, so that's one thing. Now, okay, so of course, I won't use it, but immediately from this Poisson summation formula and the fact about Fourier series of exponential of Gaussians, as I said, you can get the following nice formula, for example. Now, what is this formula? Start with any lattice in Rn, and let M be Rn mod gamma, your quotient space, and you have two sums. In fact, you have absolute equality of two sums. So this is indeed a trace formula. So on the right-hand side, this gamma star, elements of the dual lattice, those elements, those vectors that pair integrally with gamma. And of course, we know that this gamma star parameterizes a spectrum of the Laplacian on the torus, on the quotient Rn mod gamma, right? So this sum is essentially a trace of exponential of minus t Laplacian. Right-hand side is, right-hand side is just lattice sum. But then the volume of M appears, and this famous 4 pi t d over 2 factor appears directly from this thing, as I said. So, I mean, again, this is a trace formula. The right-hand side, you can say that you're summing over periodic orbits, actually. And the left-hand sum, you're summing over all the spectrum. So this is something that relates classical mechanics, you can say, to quantum mechanics, and it's a kind of very famous trace formula, approximation formula. Sorry? Volume of M is the volume that's induced by this induced metric on the quotient space. So that's really, okay, you can say it's really the volume of fundamental domain for your lattice in Euclidean metric. That's exactly volume, yeah. Okay, so that's what I wanted to say so far. Now, okay, let me give you another warm-up example for things to do. That's about zeta values, okay? So zeta values are quite they appear everywhere, as we know. I mean, now we know that they appear in Feynman integrals, Feynman motives, and all these things. They involve zeta values. But let me be very, very pedantic and start from first steps. So imagine you want to compute this number, as Euler wanted, in fact, up to few decimal digits. Okay. So this is a slowly convergent series, right? So this is very, very slowly convergent. So to get it to 6 decimal places, you have to add 1 million terms. It's very easy to see that, right? So it's a slowly convergent series. But Euler knew that zeta of 2 is exactly, I mean, the first computation of Euler after several years was this number, 1.644944. How could he compute this? Okay, but now this, he did it before summation formula, before Euler Maclaurin summation formula. And let me tell you what it is. Again, I won't use this one, but Euler had this identity, proved an identity like this. Zeta of 2 is equal to log 2 squared plus 2, this one. I mean, there's no way one could guess this formula if you don't have really some good ideas about what you're doing. But look at the formula. The formula on the right-hand side, this is a rapidly convergent series. This is geometric series. Yeah? The terms are rapid decay. This is a geometric series. It's exponentially fast decaying. So this is very easy to compute. And of course, they had access to log tables, as we do. So this can be computed with just few terms. And that's how we did it. But then the source of this equation, this computation, which is this equation, is really this dialog function which Euler introduced. So dilogarithm function Li2 of x is the first kind of family of these dialogues, trilogues, and polylogues. This is the first one. And you have this amazing relation between dialog and log. So this is a functional equation. Li2 of x, Li2 of 1 minus x, plus log x, log 1 minus x equal to Li2 1. Notice that Li2 1 is indeed zeta 2. That's by definition. Li2 1 is zeta 2, and put x equal to half, then you get this equation. So this equation is very, very special case of this dialog equation that was discovered by Euler. But Euler knew much more about zeta values. Let me just give you another number just to intrigue you. So for example, if you open any of his books in calculus, you can read the values of zeta functions at 2, 3, up to 23 with at least 15 decimal digits. Okay, so it's clear that, I mean, for example, this zeta 3 is more or less from his book. I mean, so it's clear that you cannot use those dialog functions to compute such things. Okay, so how we could compute these things? No Mathematica, and in fact, Mathematica is completely useless to compute it. You cannot use Mathematica you cannot use any computer just if you don't have these good ideas to compute these things. Okay, how he could compute it? Sorry, what? Sorry. Really? No, we did it. We didn't get it. But they used. No, we got zeta of 2n's, which is kind of built-in pi values, and then you have approximation for pi. Okay. Well, it's not. He has used Euler's techniques. Let me tell you how they computed this. Yeah. So the technique that I'm going to use actually for the rest of the talk and all these things we are using and other people have been using for calculations is really this Euler Maclaurin summation formula. So this is really an amazing formula that relates a sum, discrete sum, to integral, and then gives you very good kind of remainder terms and then higher order approximations to the sum. So this is something that unfortunately is not taught in calculus classes, but this belongs to a good course in calculus, really. And remember, these BJs are Bernoulli numbers. So Bernoulli numbers, I will introduce them carefully later on. But what we tell students in calculus is only these first two terms. You can approximate sum by integral, integral by sum. OK, this is maybe trapezoid rule. If you are a little more careful, you introduce next term. But this time we never tell students. These Bernoulli numbers never come into discussions, but this is the remainder. So using this, apply to function 1 over x cubed, and so you can compute these things without much work. So that's my kind of introduction to this calculation. So calculations really more interesting, I came to notice, than proving general theorems, actually. I mean, proving general theorems can be much easier, actually, than doing real calculations. Okay, sure. This is warped, or if you want, kind of asymmetric. metric. This is, okay, so I felt compelled to give the full name. I mean, because in the papers, we write Robertson-Walker, but I mean, Friedmann was first, of course, and then Lemaitre, and then Robertson-Walker came later. But they did different things, I suppose. I don't know the history very well. But okay, so this is the metric of kind of relativity theory. So this is a metric which describes a homogeneous isotropic expanding or contracting universe. With, in our case, we look, because we have to be compact, we look at a spatially closed universe. But this essentially tells you a kind of universe where at each instant of time, the space section of the universe is a symmetric, I mean, has constant curvature, so-called highly symmetric space has constant curvature. So in our case, this Z2 is the round metric, and then this scale factor, AT, this changes with time, and that gives you the rate of expansion or deceleration of the universe. So if you want, for AT equal to sine t, you get really round metric on S4. So this is the equation for the round metric on S4. So I have just replaced dz squared in some coordinate system. The rest is this, and AT scale factor in this case is sine of t. So this is something. And this is a picture that I stole from Wikipedia or somewhere, I don't know, from the net. So you can see this is kind of initial phase, and this is kind of expanding universe. But OK, so but expansion is linear, which is not quite correct, but it's it's not a bad approximation. OK, now references for these two works. Of course, I mean, we started from Chamseddine and Connes papers. They have a paper, on the subject, a spectral action for Robertson-Walker metric. They did a lot of things for this metric. And then we picked up from their work and then did answer some questions and did some more calculations. So these two references are kind of basic references for the work. So one of the tools that we use, as I said, is Euler Maclaurin formula for, and we applied Euler Maclaurin to compute the, okay, so this is something known, but let me just, as a warm-up, tell you how to use Euler Maclaurin formula to compute the heat kernel for S4, around the sphere. So this is the formula, turning a sum, like if you want to compute trace of exponential of minus t Laplacian or t Dirac squared, whatever. Just use this integration and this first approximation and higher order approximants. And then these Bernoulli numbers are, of course, the famous Bernoulli numbers. This is the generating function for all these Bernoulli numbers that appear in the equation like that. So that's classic. So if you look at the Dirac operator for around the spore with standard spin structures and these things, so the eigenvalues of Dirac are plus minus k, and multiplicities are polynomial, cubic polynomials like that. And as a result, eigenvalue of this square is k2 with these multiplicities. So there's a doubling going on. Okay. So then to apply this, to compute the heat kernel and all the coefficients of heat kernel, you just apply this Euler Maclaurin for this function, with this function, which is directly dictated by the multiplicity function of the eigenvalues. Okay, f of x is exponential. That's the heat part, and this is the multiplicities of the thing. So. And then the computation is very easy in that case. You can compute all integrals, I would say, almost by hand in this case. And then you get this formula, everything together. You have this asymptotic expansion for the trace of the heat operator near 0. So this is 1 over t squared. This is the pole part of order 2, which is expected. This is order 2 operator on this 4-dimensional space. So you should have a pole of order 2. Minus 1 over 2, this term is related to scalar curvature, and then this is the constant term, and so on. So we go on. Okay. So you get the complete expansion in terms of Bernoulli numbers. So that's a warm-up thing for the calculation. Now, if you want, you can also write a formula for, this is a standard, yeah. I mean, you can also write Euler Maclaurin. You can use Euler Maclaurin to compute the spectral action for S4. So in this case, the formula that you get, we get, so okay, scalar, spectral action normally is written in terms of d over lambda, but 1 over lambda is essentially t or root t or something. So we just compute it in this term, and then this is the part, and this is the constant part. So this is the part that essentially gives you negative terms, and then these are all the higher order terms. So yes, this is the result for that. Now, but okay, so these two sample calculations, just warm-up cases that has already been done, I showed you, they all really, they're used. So first of all, one of them was for a special AFT, was for round the sphere. The other one, it was also a special case. So the questions, I will tell you what the question was, the motivating question was in the paper of Chamseddine and Connes that got us going. But you really want to have a different method of computing the coefficients in order to answer the kind of rationality questions. So for this, let me remind you how you can go about computing essentially a spin connection, Levi-Civita connection, and a spin connection using frames. So you have to forget about using coordinate systems. In this business, coordinate systems are not effective enough. You use frames, orthonormal frames. So theta t is a frame for the tangent bundle, is an orthonormal frame for the tangent bundle. And the dual frame or co-frame is theta upper alpha. And then connection 1 forms can be defined if you covariant differentiate theta alpha, and then you just write it in terms of your basis. Okay, so this covariant derivative extended to the cotangent bundle, which is an obvious extension. So then you get this basically you get this connection matrix. And if the matrix is, if the connection is metric compatible, you get this condition. Now you have Cartan equations. So basically, Cartan equations gives you torsion and curvature 2 forms in terms of this structure constants of the thing. So the torsion is defined by this equation, and then if it is torsion free, this is the condition that we get. So everything should be worked out in this case in terms of frames and co-frames, and in terms of this Cartan formalism. Okay, now so to get the connection 1 form for this Levi-Civita connection, you have to have, okay, so that was the last slide was just the general thing, but you have to have some actual basis for this sphere. Okay, so the sphere is really around the sphere. It's just that the metric scale has changed by AT. Okay, the basis that they used and we used also is this co-frame basis, dt and so on and so forth. So this is written. And if you do the computation that's dictated by last slide, then you get this for the matrix of matrix connection, basically the matrix of 1 form that gives you the Levi-Civita connection. So this is the matrix that you get. Okay? And it's not a bad calculation going from there and applying covariant derivatives in using the frames and then getting this. So this is the metric you have. Now you have to lift the metric from tangent or cotangent bundle to bundle of spinors. To do the lifting, as you know, of course, you just use this isomorphism between tangent bundles of the 2 groups. The Lie algebra of SO4 is isomorphic to Lie algebra of spin 4, and there's explicit isomorphism, mu. You go from this Lie algebra to that Lie algebra. And if you write the isomorphism in terms of some orthonormal frame is going to look like this. This C is Clifford multiplication. These are 1 forms. Okay, so we can define Clifford multiplication, but forms also, not just vectors. And these are the things. And these are the coefficients. So this is a quadratic expression in Clifford algebra, if you want, or it's just the part of the realize a spin group also inside that, inside the Clifford algebra, and that's the form of the connection that we get. So now, in this orthonormal basis, we have these values of theta alpha. So you have this equation, which is by definition, you have the equation. So the connection for one form for the spinor connection is given by this expression now. These are these gamma matrices, and these are the connection one form, connection coefficients, omega ij's of omega alpha betas. So you have to calculate these. Now, the next thing that you need, well, actually, we don't need Gilkey's formulas. Yes, we don't need Gilkey's formulas, right? We just use pseudodifferential calculus. We just bypass Gilkey's formulas. But some calculations, you have to use Gilkey's formulas. So in the paper I was talking about, in the paper of Chamseddine and Connes, they have three methods of computing these coefficients. A0, well, A0 is easy. A2, A4, A6, so on. One of them is they just use these Gilkey coefficients. The other one is they just use a Brownian bridge, kind of Feynman-Cutts formula. I think there is a third method also, which is very, very interesting. They decompose the operator in terms of small pieces, and then they put together those pieces. So there are these three methods. Each method has some advantages, but at the end, I mean, this is a calculation. I mean, computers can easily make mistakes, and these things can go wrong, really. So you have to be very, very careful. But in any case, Gilkey's formula for essentially kind of Laplace type, so to speak, Laplace type operators, P, which you can write it as nabla star, nabla minus E is endomorphism of your bundle. These are these famous Gilkey's formulas that was mentioned. So essentially, all the coefficients of the asymptotic expansion of the heat operator and this operator, in this case, e to the minus Tp, are given in terms of curvature tensors and covariant derivatives of curvature tensors. So there are universal formulas. I think Gilkey has it up to term A6 maybe, or A8, I don't know. So A6, yeah. And then these things, I think, has been computed into A8. I'm not sure it has been written down explicitly up to A10 even, but Dimitri's handbook maybe has something. Yeah, there is someone who had done A8, I guess. There to look at A8, but okay. Okay. Right. Right. So for yes, okay. So for the Dirac operator, this squared, this is because of this Weizenburg or Bochner formula. This squared is nabla star nabla. We know this operator E, which is 1/4 of scalar curvature operator. So this E is 1/4 of scalar curvature operator. So anyhow, these formulas you have to work with it to compute those terms. So these are some of Chamseddine-Connes computations. So they used, as I said, one of the methods was they used Gilkey's local formulas to obtain these terms. Of course, there cannot be any other parameter except this AT, the scale factor. Everything depends on the scale factor, right? So you get that. And they even looked at A8. A8, of course, there was no formula. So the A8, they had to compute using Euler Maclaurin summation formula and also Feynman-Cutts formula. Yeah, this third formula I mentioned, by decomposing the operator, really, then they use Euler Maclaurin in each piece. And there was quite a difficult task to do in that case, but they managed it. And this is the term A8 they got. And then they made sure that the three computations actually matched. And that's the term A10, by the way. So they computed A10 also. So this is all in their paper. I mean, you can just look at it. I mean, and check that I just stole from their paper. Yeah, there is some. I just directly copy paste from the paper, so I don't. No, No. 3 methods have been kind of, and actually the 4th method, our method also now, just so these are really waterproof computations. They are very robust computations. Okay, so that's A10. Now, question? Yes, exactly. That's thanks, Farzad. Yeah, I mean the fact that these coefficients are rational like that is is irrational. Exactly. The fact that coefficients are rational is very irrational. Yes. No, not just that. No. I mean, certainly that plays a role, yeah, but no. It's much kind of more involved, yeah. Yes, indeed. Indeed, that's a very good point to mention, that this rationality of these things. So one of the things, of course, they had other reasons to do these calculations. I think they're going to work. But okay, they have some conjectures and some questions about it. One of the things was to check that these formulas for A8 and A10 and universal formulas actually match. And but the second thing is really a much more, I think, kind of very interesting question. This is the rationality statement. Up to this overall factor, well, I mean, there is a factor in the denominator. I mean, this comes out because of determinants of the thing. So this disappears. This part is unavoidable. But apart from that, there are these kind of polynomials with rational coefficients in terms of this scale factor A and its derivatives of the order 2n. That comes into coefficients, right? I think the reason they guessed this is by looking at those examples that they computed that, and but they guessed that they conjectured that this is true for all coefficients in all orders. Actually, we show that we divide by a to the 2n minus 3, I think, right, eventually. But in this case, but there should be a division, yeah, because of determinant terms.
Would you write this polynomial is also in A, or should it start with derivatives?
Oh, it is in A prime, and A to n derivatives. Yeah? No, they're not. Yeah, that's okay. That's ambiguity pays off sometimes because it just, it's economy of the okay. So yeah. Sure. Yeah. Okay. Sure. It's p of okay. Yeah. Okay. P of x1, x2, xn for x1 equal to a, x2 equal to that, and so on. Okay. So these polynomials indeed are. Okay, so it's not polynomial in one variable, it's polynomial in this variable. Okay. Now, how you're going to prove such a conjecture, so that's where essentially where the point we got in. I mean, these recursive formulas, the more you look at them, less you gain. I mean, this is just, there's nothing in this general recursive formulas that you can gain any insight from. So we decided to go to the original method of computing these things, which is pseudodifferential calculus, and just completely avoid Gilkey's method, formulas, everything. Just start from pseudodifferential calculus, solve the resolvent equation by brute force, and then see if you can see anything in the formulas, and then see what happens. So that was our method. That was essentially our method. So okay, so this is the approach is then totally different from the approach that was taken by them. I mean, this is the pseudodifferential calculus, but again, it's a standard approach. Also, the approach that we used for this noncommutative torus, and then other things. So, okay, so.
Just a question: why using Dirac operator, not Dhas?
Oh, because I think Dirac is more interesting. Dirac is, is a square root of. I don't know. I mean, Dirac is definitely more interesting. It has more information, right? I mean, it's a generator of K homology also, but Laplacian is not. So it's kind of. It could be. I'm not sure, but there is this term.
More insight by looking at I agree with you that the Dirac
But there is this extra term. If you square this d2, you get this curvature term, which is not constant. I mean, yeah. I mean, no. I mean, this is not. Yes, that's. Yeah. In the case of I mean that's bound to be because Dirac is really K-homology. I mean, it's much more subtle object than this just the Laplacian. Yeah, definitely. Okay, so then what you have to do, okay, so do this spectral analysis. So compute symbol of Dirac. Well, symbol of Dirac is this. So, I mean, this is because we have the expression for Dirac in terms of, this orthonormal frame or whatever. So you can compute the symbol, X and C. This is the explicit formula for the symbol. That's okay. And then you have to start, okay, so then, okay, yeah, it's really a symbol of D2 that you compute. Okay. So, sorry? Well, Dirac Laplacian. No, Dirac Laplacian. Yeah, but there is this extra term. Yeah, sure. I mean, of course, I mean, it's a heat kernel, so we have to apply to this positive operator if there's no way around it, yeah. So the symbol of this has 3 parts. This is the quadratic part, the leading part, this second order operator. So in the quadratic part in C1, C2, C3, C4, there's a linear term, and there is this constant term. I mean, look at the constant term. I mean, the constant term is quite substantial. I mean, okay, so it's you get this. So once you see the symbol of Dirac, d squared, I mean, Dirac Laplacian, then the equation you have to solve is this, to find the parametrics, is this resolvent equation. So the equation is P minus lambda times this formal inverse, let's call it R tilde of lambda, equal to identity. So this is in the world of pseudos now. Okay, so now you have to use multiplication formulas for pseudos to find symbol of R tilde of lambda term by term. So start with term of, okay, so I wrote R0, but this R0 is really a pseudo. I mean, it's really things of order -2. And then you have R1 and R2 and so on. So there's a recursive formula for Rn's in terms of the original one. So this is the original one, which of course we know the leading symbol of the inverse is inverse of the leading symbol. So this is not a problem. So you get R0, which is that term. But then you get equations for higher order terms. These equations are extremely difficult to analyze. I mean, this. Okay, so to see something in these equations took a lot of work, and I mean, I should say, I mean, I should really give major credit to Farzad and Asghar, I mean, for doing this amazing work. I mean, not just symbolic calculation, but just looking at formula, see if you can see any pattern in that. Okay, so then the heat kernel can be computed, of course, if you know this term by term. You evaluate, you use quotient integral formula. You invert this, you essentially write the symbol, the formula for quotient integral form exponential of minus t d squared. So you have 2 integrations to do. One is a counter integration, and the other one is the integration over the momentum space. So once you do that, you get these terms ENs. These are these. So ENs, these integrated things, comes out to be of a certain form. There is a sine of this one of the coordinates and sine of theta another coordinates, and then these coefficients C alphas are products of gamma functions, I mean gamma values of this form, and then there is this scale factor that comes. So there is some structure here, but okay, so you have now to integrate this again. So AN, eventually, the heat kernel coefficient is a triple integral of this EN over the 3 sphere. So essentially, you have to compute this over the 3 sphere now. Okay, so the thing that we did, the computation was done for A12. Okay, so they did all the computations up to A10. They all matched on the nose with Chamseddine computations. Okay, so that was very good. And then the new term that was computed is A12. So the term A12 is here, but that's not all of it. There is. Don't relax. The remainder is there. Okay. Again, there are these rational terms. But of course, this is only up to A12. Who knows what's happening after that? OK, so maybe for a physicist is a proof. But for a mathematician, this is not a proof, of course. You want to see really how it goes. So the real thing was then to try to prove it. But OK, we did some checks, actually, with their computations also with some checks. I mean, these checks involve some computing some of these, I mean, these coefficients. So these are like density. These are functions over the sphere. And then you really do get their values on the nose. So that was basically the stage. Then we were kind of stuck. We didn't know how to prove this rationality. That was like till maybe 6 months ago, I think, 5 months ago, something like that. And then, to see the rationality, you see a lot of patterns in these things. But then at the end of the day, what happened after a few months, what happened is that we noticed, well, they noticed that you can break down the whole things into 2 parts. There is one part that you can show it's rational. But there is another part which is not obviously rational. It's the second term, which was the bad term, was some combinations of different powers of pi to different powers with some integrals. Okay. So that term obviously is not a rational term unless the coefficient of each of those pi powers is 0. Right? So the coefficient of each of those pi powers has to be 0. Because the other ones, up to an overall factor, you could show that this is rational. But the other terms that it was not rational was some pi powers, but different powers of pi, some integrals. So that those integrals have to be 0. So then the question was really why those integrals that are part of this kind of heat kernel coefficients are 0. So so this is kind of actually the theorem. So let me go. I'll go back to the proof, but this is really the theorem of the proof. As I said, we really prove with 1 over at to the power 2n minus 3, right? So 2n minus 4 doesn't appear. This 2n minus 3. And this polynomial, we have a very good idea about the structure of the polynomial, I think. OK, so up to some terms, not in general. So the structure of polynomials are still very interesting. We can say something about it, but we can say that all of them are rational, for sure. And the last stage in the proof, as I said, was the vanishing of these integrals. And so when you see vanishing, you must think about what? You must think about symmetry. Of course, vanishing is always an artifact of symmetry. If you have a symmetry, something is vanishing, or vice versa. This is infinitesimal symmetry, vanishing, right? So then we thought that, OK, there should be some symmetry in these things that make those parts of the heat kernel actually vanish. And in fact, so I was lucky because that term I was teaching a course on differential geometry. So all these killing vector fields, equations for curvature, for Lie groups, those terms was kind of fresh in the mind of all of us. So then we thought about it. Then we could find actually the symmetries. In fact, what happens is that you have to find explicit basis for left invariant and right invariant vector fields for SU2. This is 3-sphere. Integration is over the 3-sphere, as I told you. So you have to find explicit basis, and then you have to show that when you apply this sort of leader. OK, so the thing is symmetric with respect to this SO3, definitely, or action of SU2. But then you have to show that exactly those terms appear if you apply the Lie derivatives. And if you apply these things, you get all those terms exactly as the result of applying these things to those terms in the heat kernel. And because of symmetry, you know that they have to be 0. And that's exactly the terms that you want to be 0. And that's how the rationality was eventually proved. So we can say that proof of rationality in general was not a result of computation, but was also a result of computation, because we had to see a structure in terms, because you had to separate terms into different parts, and some parts was related to these things. The other parts, they could show directly that it's rational. So, OK, so the argument is quite involved. I mean, you have to see the structure of terms. I mean, there's quite a structure. What we still don't know, I mean, is what is the general form of this Q2, and I believe this is an interesting problem to find the general form of Q2n. I mean, certainly rational coefficients We know a little bit about it, but we don't know as much as we wish to know. So that's a kind of thing. So, of course, I mean, this was just, I think the whole thing is really warm up. Now you want to apply what you gained, the information you gained about these things, to do something with this kind of metrics, right, with this information. Okay, so this remains, I mean, so let's, okay, so we have some ideas, but we have to do it first before saying anything about it, I think. So it's a Friday, you're all tired, so let me just stop and thank you all for listening, yeah. Yes.
So they are essentially polynomials in the Euler curvature. There is nothing else here.
Yes.
And the Euler curvature is rational, right?
Riemann curvature tensor, you have expressions, I suppose, yeah.
And therefore,
but I mean,
just multiply a lot of rational functions, you will get rational functions.
This we could not see it that way. I'm not sure if it is really obvious like that, because you have to integrate, and then some of the integrals. I mean, you have some combinations of powers of sine and powers of cosines. You integral between 0 to 2 pi. Then some powers of pi shows up, but with different powers. And then you add them, you group them. I mean, certainly you cannot expect. I mean, the coefficient of those pi powers are rational. But pi themselves are not rational, and they come with different powers. But then, why those terms vanishing? So it's not, you know what I mean. And so this, we can.
So that's the issue that you should actually integral is stereo.
Yeah. This is the. Yeah. This is where all really mixed up. That's where the thing is.
Another big comment that's well, I can give kind of theory. So if Gilkey's original method of calculating typical coefficients works, then all the coefficients inside are rational numbers. I mean, it's just, well, it's built in such a way, so you have something which is absolutely obvious in this immediate expression. Like you have term which is A100,
well,
100, then you know that E to 50 has a coefficient 1 with 50 short.
Coefficients? The coefficients of Gilkey are rational. I believe so, yeah. But these are densities, right? This just gives you densities. You have to integrate the densities and to get rational numbers. No. I understand. No, sure. Yes.
I don't know what will happen when you integrate them.
That's right. Yeah. Sure. Yeah, that's right. Yeah. I realize. Yeah. Sure.
Just one question. You did it for a sphere.
Well, this is a warped product. I mean, it's not really a sphere. I mean, it's really the two things are kind of is warped.
For the thing with this sort of a suspension or something like other three-dimensional manifolds, not a four sphere, but something like say S1 times something or some suspension or some other.
I think calculation, I mean, will go through up to 8, 10, 8, 12. I think that calculation will go through. I think it should go through.
Should be the same type of result.
I think should be, but rationality, I don't know. Rationality is completely, I mean, this is something which is really, I mean, these integrals of different powers of pi, and they all, each individually, the coefficients are 0, and they are sums of many terms, by the way. And that comes from the symmetry, so, okay. So that was the thing. Yes. I see. Yes. Yeah. Sure. I mean, this is the kind of densities. Yeah. I mean, kind of. Yeah. I believe. Yeah. I mean, sure. I mean. Yeah. Of course. No. I agree. I mean, the comment is correct. Sure. Totally. I see. Well, the odd terms are in this case they are 0. They're not. They're not there. By some simple symmetry argument. I mean, if you have Gaussians and then some odd polynomials integrate over Rn, they're 0. That's the reason.
Can you say something about the use of rationality of these?
I don't know. Yes. Well, no, I mean, no, I think the rationality kind of, it's an interesting observation. I mean, you don't know what it means really. I mean, but the fact that you can make a statement about all coefficients all the way, it's interesting. But then really computing the terms is kind of okay. So yeah, no, I don't have any kind of more sophisticated comment about that. No. Yes. Yeah. No, it's not. Yes. Yes, I think. Yeah. Okay. So if you do quantum field theory with this, then perhaps rationality maybe can be understood from I don't know, Feynman integral point of view or something. I don't know. I have no idea.
Could we expect some similar results not when you compute the expansion
Well, that depends on f, of course. Some yeah. Okay. So yes. Okay. So for example, has rational moments, things like that. Yeah. I suppose. I mean, I'm not sure. We didn't look at that. Yeah. Just looked at things. Yeah. There are formulas, right? By this Laplace transform, you can always write this Chamseddine formulas, right? Oh, I see. Okay. So yeah, it might be feasible. Yes. Yes. Yes.
So, is it possible to compute the Zeta values using just the Poisson summation of Euler Maclaurin in order to
No, there is no. I mean, as far as I know, Poisson summation cannot be used for Zeta values because I mean, there's no group structure there. I mean, you can use Poisson summation anytime there is a group structure. Definitely, you need a group. You need an abelian group actually. Okay, so it would be nice to use trace formulas for cell-break trace formula to compute some spectral actions. I mean, so for Riemann surfaces, sure. But okay, that would be an extension of Poisson summation. Yeah. But I mean, again, indeed, Poisson summation is really backbone of modern number theory. I mean, also, that's all of Tate's thesis is based on Poisson summation. So that's. I mean, all of class field theory, basically comes from that. Functional equations for Dedekind zeta functions or everything.
Actually, you can get actually the only fifth kernel or odd dimensional spheres or even dimensional spheres you can get for some summation, and for other pairs the dimension you have to use so you can.
I see. For odd dimensions you have Poisson summation. Yes. I see. Okay. I see. Yeah. Yeah. I think it's 4. I have this. No, I mean this is really. Well, thanks. Thank you. Yeah.